Bismillahirrahmanirrahim. My name is Mohammad Umar, and my group members are Mohammad Ahmad Wasim and Taha Afzal. Today, our topic of discussion is Brownian motion and its applications. When you go to the stock market and see the price of shares of your favorite brand, the following thing will be observed. This is totally random. This is one scenario. There are many scenarios, and each path is known as sample path. Now, the question here is how to model this zigzag path. Is there any mathematical way to represent it? Can I construct a stochastic process? Sample paths are represented in this form. The answer is yes. To do that, we need to study what is called Brownian motion. Robert Brown was a botanist who made important contribution to botany largely through his pioneering use of microscope. His contributions include one of the earliest detailed description of cell nucleus, cytoplasmic streaming, the observation of Brownian motion, early work on plant pollination and fertilization. Next, please. Brownian motion, next slide. In 1827, while examining grain of pollens of the plant suspended in water under a microscope, Brown observed minute particles now known to be starch organelles and lipid organelles ejected from pollen grain, executing a continuous rotary motion. He then observed the same motion in particles of inorganic matter, enabling him to rule out the hypothesis that the effect was life-related. Although Brown did not provide a theory to explain the motion, the phenomena is now known as Brownian motion. Next slide, please. George Gamow was a Russian-American theoretical physicist and cosmologist. In his book 123 to Infinity, he said that water is far from still and that its molecules are in state of violent agitation, moving around and pushing one another, as though they were people in highly excited crowd. This irregular motion of water molecules or the molecules of any other material substance is known as heat or thermal motion. Although molecular motion as well as molecules themselves are not directly visible to the human eye, it is molecular motion that produces a certain irritation in the nervous fibers of the human organism and produces the sensation that we call heat. For those organisms that are much smaller than human beings, such as, for example, small bacteria suspended in water, the effect of thermal motion is much more pronounced. And these poor creatures are constantly kicked, pushed, and tossed around the restless molecules and that attack them from all sides, giving them no rest, as you can see from the picture. This amusing phenomenon known as Brownian motion, named after the English botanist Robert Brown. Next slide, please. Similarly, Burton Malkiel is an American economist and writer, most famous for his classic finance book, A Random Walk Down Wall Street. In his book, he said that a random walk is the one in which future steps or directions cannot be predicted on the basis of past actions. When the term is applied to the stock market, it means that short-term changes in stock prices cannot be predicted. Investment advisory services, earning predictions, and complicated chart patterns are useless. A book named The Drunkard's Walk by Leonard Mlodinow is an American theoretical physicist, screenwriter, and author. In physics, he is known for his work on large N expansions, a method of approximating the spectrum of atoms. In his book, The Drunkard's Walk, he said, the drunkard walks refer to the random motion of molecules suspended in a Brownian fluid, continuously bumping against each other. This incessant scramble leads to the movement of molecules that is hard to predict, but can be confidently explained after the fact. Metaphorically, the drunkard's walk is a path punctuated by random impacts and unintended consequences that result in life-altering event. Next slide, please. Now, in order to understand the Brownian motion, let's begin with the simple stochastic process, that is metric random walk, where there are only two possibilities. You can either go up or down, like a coin toss, head or tail. Take a fair coin and keep on repeating tossing it. So this is stochastic process generated by repeated tosses of fair coins. Next slide, please. There will be a large number of scenarios. One of them is given in the result in the previous slide. Constructing a random variable xi, which can take the value 1 when omega I is equal to head and minus 1 when omega I is equal to tail. Next slide, please. Now, we will define a stochastic process, mk, which is plotted here. It is the result of summation. For example, at point 0, there the output is tail, so the value is 0. But at 1, the output is again tail, so minus 1. So 0 minus, 0 is added in minus 1, so it is minus 1. Then at point 2, the outcome is head, so 1 is added in the total result. Minus 1 plus 1 is equal to 0. So from this way, the whole graph is plotted. That's all from my side.
Assalamu alaikum everyone, this is Taha here. Now we will move towards second basic concept needed to explain before Brownian motion, which is Markov chains. As written on the slide as well, that the Markov chains determines the probability of a stochastic process from one state to another. Let's suppose if your starting state is I, so it tells you the probability that your next state will be J. And all the states are independent of each other, so no future state that depends on the past state. The future state only depends upon the present state, that your present state is I, so the next state will be your J, and the probability will be told by Markov chains. And it is the third axiom of probability as well, that sum of all the probabilities is always 1. Next slide, please. So as now we have discussed two basic concepts of Markov chain and random walk, now we can briefly describe Brownian motion. Brownian motion is a real valued stochastic process whose value is 0 at the starting instant. That is written on the slide as well, that W of 0 is equal to 0, and it always has independent increments in it. The time is always will be greater than 0, and every increment will be independent of all other increments. It always will have a Gaussian distribution with following parameters, that its mean will always be 0 and its variance will be the time instant. And let's suppose if it doesn't start normally in a real world, Brownian motion doesn't start with 0. So if it doesn't start at origin, the only change in Brownian motion will be its mean will be shifted by that number. Say if W of 0 is equal to m, the mean will be shifted by m. Next. Here is the visualization of Brownian motion as we have described it in a theoretical language, that what Brownian motion is. This is a graphical visualization of Brownian motion. As you can see that we have plotted thousands of Brownian motion, from which we have just selected 5 of the Brownian motion in this graph. You can see clearly from the graph that the mean of the Brownian motion is equal to 0. As you can see the straight line in the graph. Now, how we plotted this, it will be in the next slide. How to create a Brownian motion. Here are the steps to follow. First, you have to assume a starting point. And we have studied that the starting point just doesn't affect our Brownian motion. So let me assume a starting point. Next, we have to calculate that how much points we want that Brownian motion will include this much points. That is described by a number n, that is equal to total time divided by dt, and dt describes the increment, that is the scaling of your graph, that how much increment you want in your time, and capital T is the total time lapse, that how much for which duration of time you want to plot your Brownian motion. Then you have to start iterations from 1 to n, and then you can plot the Brownian motion using equation given in the last point. And now you can plot how many Brownian motions you want to plot. You can plot using these equations. Next. As now we have seen that how to plot Brownian motion and what Brownian motion is, now we can describe the properties of the Brownian motion which it possesses and which makes it interesting. That standard Brownian motion is always distributed normally, and it will always have 0 mean and variance. And we have also seen that if the mean is not 0, it doesn't bother us. The next interesting property of a Brownian motion is that the steps taken by the process are always independent. So the increment in the time intervals will always be independent. As the processes are independent, they do not affect each other. So as we have studied in Markov chains and random walk as well, that the process is independent, so we can easily use Brownian motion in such type of processes in which the processes events are independent to each other. And the third property of Brownian motion is that the length of the interval is independent of the time, and it is independent of the time instant at which it begins. It begins at origin, it begins at somewhere from where else. It doesn't bother Brownian motion anywhere. The next property is that if there is we have to calculate a variance of a motion. Let's suppose there are two time instants t1 and t2, and I have to find the variance between t2 and t1. So we can easily add the variance at two time instants. It will give the value of the Brownian motion, that is a variance of wt2 plus t1. And it is also written on the slide that it's simply equal to variance at t2 plus variance t1. Next. Now, where the Brownian motion can be used. Brownian motion has so many applications in real world problems, as normally in real world processes are not so much independent to each other, as there are so many factors which makes it processes dependent on each other. But if we assume things independent, it will make more easy for us. So interesting features of Brownian motion makes it helpful in making decisions in different situations of real world. Some of the applications are like stochastic calculus. Stochastic calculus is a branch of mathematics we in which we model the system using integrals, and the integrals are behaving randomly, so we can use Brownian motion in stochastic calculus. The next one is diffusion process. As we know that diffusion's basic definition is the random movement of molecules in fluids. So as the molecules of the fluids are moving randomly, and their movement is not dependent on each other molecules movement, so we can use Brownian motion in diffusion processes. But the only difference in diffusion processes is that we use differentials of the movement instead of integrals. Like as we know that calculus is all about integration, and in diffusion process we use differentials. The next application of Brownian motion is quantum physics. In quantum physics, as you know, that we study the movement of particles found in an atom, and there are so many hundred above particles in an atom, and all are moving every time they are moving or they are vibrating. So their movement is random, and we can find the trajectory of the particles using Brownian motion in quantum physics. That the trajectory of the particle is independent, and it is also random, so we can use Brownian motion in it. Then the next application of Brownian motion is in electrical engineering. As we all know that in making filters there is a factor of noise which we want to eliminate. So we can model the noise factor using Brownian motion. As we know that the noise factor is also random, and when we add so many random variables, it results in a Gaussian distribution. And Brownian motion also has a property of Gaussian distribution, so we can use it in electrical engineering as well, while making any system, while modeling any system in which there is a noise or there is any error which we want to eliminate. So we can use Brownian motion here. The next application will be finance, and from here I would like to invite Ahmed to proceed the presentation from here.
Thank you. Assalamu alaikum everyone. I'm Ahmed. So, as Taha told you earlier, that there are many applications of Brownian motion, but we will focus more on finance. So, in finance, you will everywhere found a very important model or very famous model known as DSM model, named after these scientists, Black, Scholes, and Merton. And for presenting this model, they even received a Nobel Prize in 1997 in economics. And this model is basically based on Brownian motion. So now we will further discuss how you can use Brownian motion actually in making decisions in finance. So the Brownian motion is quite helpful as it varies non-linearly, and it has very random type of motion. And just like stock can vary independently of at time. Like I have some value now, tomorrow its value may change independently from what value was today. So you can use Brownian motion, but there are some factors that that are must be kept in mind. The first one is Brownian motion has negative values as well, whereas the stock values can never have negative values. Moreover, the mean of Brownian motion is always zero, as discussed earlier. But in case of our stock, we have seen that there is on average an incremental effect. So to account for these two problems, we incorporate another term known as geometric Brownian motion. In geometric Brownian motion, we have used exponential term, which exponential term does the negative for very high negative terms. It takes it outputs very small positive terms. So the problem that it takes negative outputs is resolved. Secondly, we have taken a value alpha t, which determines that mean is now not zero. If you take the mean of this value, it will be exponential of alpha t, and your value will be around exponential of alpha t instead of zero. So the mean is shifted, and this accounts for the incremental effect. And the third thing is beta factor. The beta is a multiplication factor which accounts for how much variable your stock is with respect to your mean, and after some time t, how much variation you must take. Now, if you want to visualize this stock, you will have to assume initial value at time zero. Let's suppose I assume that is at 10. Then I will calculate for the total time, taking an increments of dt or how much value of alpha t. And then I will calculate omega t as before. Taha has told you. Same method will be used, and we will use same value of capital T and dt for that are used to calculate alpha t. And we find omega t and multiply it with beta, and finally we'll calculate sp. As Taha told you earlier, for same values at different instances, there are different motions that a Brownian motion can take. So if you take those and fixed values of alpha and beta as shown in this slide, your multiple instances of WT will give you multiple values of this SP. So if you take those multiple instances of SP and plot them and pick randomly five of those values and plot them, and also take their mean, you will see the mean is now not zero, it is exponentially increasing, and all values are now moving around this mean. Some are up, some are down. And suppose you want to predict in this very stochastic type of motion, you want to predict how at time t is equals to 200, you want to predict what is the probability that my values are greater than 250. So what you will do is at time is equal to 200, you take all those graphs and you see how many of those graphs have crossed the value 250, and you normalize it by total number of graphs, and you will get a probabilistic term that okay, at time 2 is equal to 50, this probability that my stock is greater than this value. In this case, now you are sure that at time is equals to 200, it is almost certain that the value will be greater than 100. So you are sure that at time is equals to 200, your stock is gonna go above 200. And all these values are based on alpha and beta. You change alpha and beta, these graphs are totally gonna change. So moving forward to a more complex problem, let's suppose I have a factory and I produce some product using multiple resources, let's say 10 resources. And you want to use those resources which are low in price, and for using which price you have some very low loss factor. But the point here is that you cannot do that. You cannot do that easily, because if you switch the value of closing and turning that on and on those sources, you have to accommodate some loss. Let's suppose I'm using some product and making it using 10 resources, and the resource one is taking me towards loss, and I close that resource. Instantly at that time, the price of that stock goes up, and now you know that I am at profit if I use that resource. Then what you do is you start using that resource, and if you switch those values of zt very instantly, you may commit extra loss. So in order to not go in that trouble, you have to formulate some optimal switching problem. Okay, so the problem here is formulated as following. You assume that the price of the resource is following geometric Brownian motion. Here you can see that it is a kind of geometric Brownian motion with a drift factor tweaked a little bit. So don't worry about that. It is just a simple geometric Brownian motion. And similarly, you have a price variable qt determining the amount at time t of that resource. And this is following the equation dqt is equal to minus lambda times dt qt dt. And what this term is saying, that the value of zt is 1 if that resource is being used, and the value of zt is 0, of that resource is not being used. And you can see easily that if that resource is not used, dqt is 0. And if that resource is being used, then your quantity is going to decay at a rate of lambda. Okay. So similarly, in this way, you can represent the state of system at time t using this vector. And if you solve this using stochastic calculus and huge mathematics, you can see that the end solution comes out to be this. You have two variables, one is psi, one is eta. And you are assuming that psi is greater than eta and both are greater than 0. Now, what this equation is saying that if the product of pt times qt goes beyond the factor psi, you should start using that product and switch the value of z, and you switch it again back to 0 when it goes back after a lower value eta. It will be clear from the figure. There are two planes at z is equal to 1, at z is equal to 0, and you are not switching at a single point, you are switching at a different point. In this way, the value between eta and psi is your waiting factor, in which you are waiting for the price. Okay, so I will wait before switching, that I do not accommodate some extra loss. So this is a very beautiful solution of using Brownian motion, and this cannot have could not have been solved if the price has not followed geometric Brownian motion. So in the end, I would just like to say Brownian motion, which was just introduced by Robert Brown from random particle of in 1827, has now indulged in finance and is now helping us in making many good decisions and many optimal decisions. That's it. Thank you, Jazakallah.